geometrical shape of metal ligand complexes. Three interaction we are going to discuss over here: sigma donation interaction in square planar complexes, sigma donation pi donation interaction in square planar complexes, and sigma donation pi donation and pi acceptance in square planar complex. Today we'll begin with sigma bonding in square planar complex. Here the square planar geometry, and when you compare the square planar geometry with octahedral complexes, octahedral geometry, only the ligand on this axial side, z-axis, this is a plane of x and y axis where ligand 1, 2, 3 and 4 are there, and on z-axis ligand 5 and ligand 6. Ligand 5 is upside of the plane and ligand 6 downside of the plane is missing. So coordination number for square planar geometry would be 4. Ligand 1, 2, 3 and 4. Metal is on the center of the Cartesian system, and sigma 1, 2, 3 and 4 sigma bonds are there. So that we are going to discuss today. I am Dr. Devang Pandya from Department of Chemistry, St. Xavier's College, Autonomous, Ahmedabad. Sigma bonding in square planar complexes. Consider the case of pure sigma bonding in Ml4 complex with a square planar stereochemistry, and this D for H, that is a point group, and work out the molecular orbital schemes as we have done for the octahedral Ml6 complexes. Only by saying this I can give this to the assignment and for self-learning, but instead I am going to explain the sigma bond in square planar complexes as well. We will follow the same sequence of 4 steps. You know that in octahedral geometry and for tetrahedral geometry as well, for all these 3 interactions we follow 4 steps. Step 1 is to identify the valence orbital of central metal ion, and we need to assign symmetric symbol, Mulliken irreducible terms to the valence orbital of central metal ion, and try to find out the LGO formation in step 2. And in LGO formation also we are going to assign the symmetric terms, and because this complex formation undergo SALC, symmetrically adapted linear combination, we are going to match the symmetry of LGO with the symmetry of valence atomic orbital of central metal ion. When the symmetry match, the overlapping will take place. So that is the things involved in the second step. Pictorial diagram we are going to represent to indicate the overlapping between the equal symmetric LGO and atomic orbital of central metal ion and their interaction. Step 3 is always formation of molecular orbital, and we will going to give the wave function associated with each interaction. And then final in step 4 we're going to generate MOED, molecular orbital energy diagram. Using all the 3 steps we're going to arrange the molecular orbitals into increasing order of energy and interaction of atomic orbital of central metal ion and LGO, and that way we're going to generate molecular orbital energy diagram, in short MOED. Step 1 already I have briefed you out, classification of metal valence orbital, and try to find out into sigma symmetry. That means we're going to assign a symmetry symbol, especially sigma symmetry labels to the valence orbital of central metal ion. Step 2 include formation of ligand group orbital, that is LGO, and because only sigma donation interaction we are going to discuss, so sigma LGOs that we can say as well. Step 3 is the formation of molecular orbitals, and we're going to generate the wave function associated with the metal ligand interaction. And step 4, using all the 3 steps, we're going to construct molecular orbital energy diagram. Let's begin with the step 1, classification of metal valence orbital into sigma symmetry. Let us choose a Cartesian coordinate system with the central metal ion M at the center, and the molecule is disposed in XY plane with its 4 sigma bonds, metal ligand bonds, along X and Y axis as shown in the figure side. You can see this is X axis, Y axis and Z axis, and as already I have said that the comparison with octahedral geometry, there is no ligand 5 and 6 on Z axis. That means Z axis does not possess any ligand, while X axis have ligand 1 and 3 and Y axis have ligand 2 and 4, and they will going to form sigma 1, 2, 3 and 4 sigma bond, and this interaction we are going to discuss today. This is D4H symmetry, and this is the character table of D4H for sigma interaction. So we must now find the representation for sigma vectors by performing all the D4H operations in terms of characters as shown in this D4H character table. Further into step 1, when we have D4H symmetry group theory, group is assigned D4H to square planar geometry, and its sigma interaction, we're going to find out the terms irreducible Molecular symmetric terms, or in other sense symmetry labels. This sigma can be reduced to A1G, B1G, EU from the D4H character table. The symmetries of the atomic orbitals can be ascertained as A1G to 4s atomic orbital of central metal ion, B1G to dz square 3dz square of central metal ion, B1G dx square minus y square, another 3dx square minus y square, the atomic orbital of central metal ion, EU to px and py, 2p orbitals, px and py of central metal ion, B2G, that is for dxy, that is a planar orbital arrangement, and EG, that is dxz and yz, and finally A to U, that is for pz. You may puzzle that in octahedral geometry the symmetry labels are very less. In tetrahedral geometry, the G and U, which is indicated over here as subscript, is missing there. And now in this square planar geometry, why this many labels are there? So for that you need to take a little help from crystal field theory. In crystal field theory, what happens when metal ion is in a free state, it has 5d orbitals which are degenerate. Degenerate means equal energetic. When ligand approach to this kind of free metal ion, its energy get increased, but yet the degeneracy restored. That means degeneracy remain as it is, but ligand come very closer. Say for example, Coulombic distance, when ligand approach to the central metal ion, the d orbital lost its degeneracy and classified into 2 groups depending on the effect of the power of the ligand approaching to the central metal ion. It may be either T2G and EG. If T2G going to be higher energetic and EG going to be lower energetic, then that is a tetrahedral splitting. If EG is going to be higher energetic and T2G is going to be lower energetic, then it is a octahedral splitting. But if certain ligand like carbon monoxide, cyanide, which have ability to split the orbital more effectively, then it's split into dz square, dx square minus y square, dxy, dyz and the zx. Out of 5, the z square is going to be singly degenerate, that is non-degenerate. The x square minus y square is also going to be non-degenerate. The xy is also going to be non-degenerate, while the xz and yz is going to be doubly degenerate. So that way the splitting in square planar geometry is much higher compared to octahedral and tetrahedral symmetry. And therefore here more symmetry level should be assigned to the valence orbital of central metal ion. So you can see there is two different color. One is in green, the other are in blue. Why it is, we're going to discuss later. As discussed earlier, the best possible combination for hybridization can be shown as DsP2. In octahedral geometry, it is D2sp3 or sp3d2. In tetrahedral geometry, sp3 hybridization is there, while in square planar geometry, it is assigned as dsp2 hybridization. That means these are the hybrid orbitals which participate into overlapping and participate into bond formation as well. So when we say dsp2 hybridization, the x square minus y square, 3d x square minus y square, 4s, 4px and 4py. These are the valence orbital of central metal ion can only participate into hybridization. So the contribution of dz orbital is there, because you know that in dz orbital the positive lobes are on z-axis and there should be a ring spread on x and y. Now why only the x square minus y square, 4s, 4px, 4py orbital only participate into this sigma interaction? Then you need to see this shape. In square planar geometry, there is no ligand on z-axis, while on x-axis ligand 1 and 3 is there, and on y-axis ligand 2 and 4 is there. That means approaching direction of ligand is axial once again, like octahedral geometry. Only difference is there in octahedral, z-axis also have ligand 5 and 6, which are missing over here. So only planar arrangement is there, and that is why we say it is a square planar geometry. So in a square planar geometry, ligand 1, 2, 3 and 4 approach to central metal ion from the axial side. And which axis? X and Y. So those valence orbital which is related to X and Y, or those orbital like 4s which have symmetry spread on all these orbital equally symmetrically, can participate into hybridization and can participate into bonding. So that you need to keep in mind, and that is why 3d x square minus y square, 4s, 4px and 4py, these are the only orbitals, axial orbitals which will participate into dsp2 hybridization, and that is the way they participate into sigma bond formation or sigma interaction, and that is why these are shown into green in color, while the rest will either going to be partially participate into bonding or either non-bonding molecular orbitals. So they are blue in color. So they will remain either non-bonding or partial bond formation would be there, as the symmetry little bit match somewhere then and then only. Otherwise they will remain as non-bonding molecular orbitals. Now step 2. So first step is to assign symmetric labels to the valence orbital of central metal ion, which is completely done. And we need to focus on the step 2, formation of ligand group orbital. And because it is only sigma interaction, so we can say it is sigma LGO formation, ligand group orbital formation. We can now construct the ligand group orbital corresponding to the same symmetries as those of metal valence sigma hybrid. A pictorial approach presented into a figure, which we're going to just see into this slide, is always simple, and the results are listed in the table given over here as well. So this is the table where this is a symmetry label A1G, which we have assigned to 4s atomic orbital of central metal ion, and its LGO formation is half sigma 1 plus sigma 2 plus sigma 3 plus sigma 4, all positive interaction, that is BMO, and when we put minus 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 sign, then it is going to be ABMO. Similarly, symmetry label B1G, B1G assigned to dz square and dx square minus y square. Both is having the same symmetry label B1G, that is assigned to dz square and dx square minus y square. Generally, dz square should not be there, but because I already have explained that on axial side, the positive lobes on dz square is on z-axis, but the ring carrying negative lobe spread on x and y axis, and that is why dz square have a little interaction with the four ligands, and that is why its ligand group orbital is formed as half -1, -2 sigma, -3 sigma, -4 sigma, because all the interaction with the minus lobe of the dz square, that is our ring structure, and that is how we're going to get this kind of BM. Now dx square minus y square, which is purely on the x and y axis, so we have half sigma 1 as a positive lobe interaction, sigma 2 is a negative lobe interaction, sigma 3 that is a positive lobe, and sigma 4 that is negative lobes. So that will going to form LGO for dx square minus y square. EU is a doubly degenerate, that is for PXY and PX and PY. PX, that is half under root 2 sigma 1, that is a positive lobe interaction, and sigma 3 is a negative lobe of interaction. We'll going to see into the pictorial presentation again. And for PY, 1 under root 2, 1 upon under root 2 sigma 2 is on having a positive lobes interaction, and sigma 4 with the negative lobe interaction is shown, and we're going to see into pictorial presentation as well. So this is how z-axis is there, positive lobe spread on z-axis like this, and negative ring would be there, and with this negative ring again 1, 2, 3 and 4 has interaction, that is why minus symbol is there. We'll see into the pictorial presentation lower in the next slide. Further into this, let's say the 4s interaction with ligand 1, 2, 3 and 4. You know that s orbital, 4s orbital is spherical in shape. It is symmetrically spread on x and y and z axis equally. So all ligand have equal overlapping, equal interaction, and all is positive in sign. The ligand sigma orbital overlapping with metal s orbital is shown in this figure, and the wave function psi a1g here, whatever overlapping will take place with 4s will symbolized with a wave function at psi a1g, and can be written in a straightforward manner since s orbital have positive sign everywhere, plus 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 on all the axes. So this overlapping will result into sigma 1 half 1 upon 2 sigma 1 plus sigma 2 plus sigma 3 plus sigma 4. So that is A1G sigma LGO. Thus the wave function can be represented as 1 half, that is 1 upon 2 sigma 1 plus sigma 2 plus sigma 3 plus sigma 4. Now the interaction of this typological mistake, d orbital with the ligand sigma orbital needs special mention since the larger lobes, that is positive lobe of dz square, here also dz square is there, dz square orbital are oriented along the z axis where there is no ligand. Ligand 5 and 6 are missing compared to octahedral geometry, whereas its smaller angular ring with negative sign is in x and y plane. So you can see obviously the ligand present on x and y axis will going to interact with the planar ring, and that interaction is going to be rather very weak interaction. The LGO wave function of dz square orbital can thus be written showing in the interaction only with its donut part, not the main lobes. These are the main lobes on the z-axis, and there is no ligand on above the plane, there is no ligand below the plane, so there is no overlapping take place with these positive lobes. but these negative lobes which spread on x and y axis equally. So each ligand is going to interact with this, and it is a partial interaction. So that also going to form sigma overlapping, and it is a B1G dz square LGO is going to be formed by this. And that's going to give a wave function psi B1G dz square as 1 upon 2 minus sigma 1 minus sigma 2 minus sigma 3 and minus sigma 4, because all the ligand 1, 2, 3 and 4 has interaction with this minus lobe spread on the x and y axis. That is why all these symbols are minus. Other LGO can be similarly formed and have the following expression, which we're going to see: psi b1 gdx square minus y square, that is 1 by 2, sigma 1 minus 2, minus sigma 2 plus sigma 3 and minus sigma 4, and psi eu, that is for px orbital, that is 1 under root 2 sigma 1 minus sigma 3, and another that is doubly distributed, that's why py is there, 1 under root 2 sigma 2 minus sigma 4. These are the pictorial presentation of the same dx square minus y square over here. So this wave function has this interaction. You can see here ligand 1 and ligand 3 have plus plus overlapping interaction with the positive pole of dx square minus y square. So ligand 1 and 3 are positive in symbol, while ligand 2 and 4 has interaction with the negative lobe of the d orbital. So again 2 and 4 represented over here as minus. Plus and minus, again I will inform you that it is not a mathematical symbol, it's just the direction of the lobes which is going to interact with ligand 1, 2, 3 and 4. So this will going to represent B1G LGO. Please remember B1G LGO, we have two interaction. One is with the x square minus y square and the other one is for with the z square. Now here we have doubly degenerate. This is singly degenerate though. That you need to keep in mind. A and B terms in the symbol symmetry labels represent singly degenerate, that is non-degenerate. E represent doubly degenerate and T represent triply degenerate. So here EU is there. U stands for unzeroed, that is unsymmetrical arrangement. PX and PY has unsymmetrical arrangement over here in this actual side. You can see this is for PX, central metal ion PX, positive pole is towards ligand 1, negative pole is towards ligand 3. So 1 is going to be positive, you can see over here, and 3 is going to be negative, you can see over here as well. So that is the way the pictorial presentation will going to represent this wave function associated with for PX of central metal ion atomic orbital, and the same symmetry we have with the LGO when this overlapping will take place with the central metal ion. Similarly for PY, you can see the lobes are spread over here in this way. The positive pole is towards ligand 2. So with positive pole, ligand 2 have positive interaction. So sigma 2 is positive, and with negative pole, ligand 4 has negative interaction. Sigma 4 is going to be shown over here as with negative symbol. So this pictorial representation represent the formation of sigma LGO in this square planar geometry. These are all the interactions with 4s. You can see all positive interaction. So it will going to form A1G sigma LGO with dz square. There is no ligand above the plane, below the plane. So with this positive lobes, there is no interaction of the ligand with this positive lobe of dz square of the central metal ion. But with 3dz square, this negative ring is spread on x and y axis. So all four ligands will interact, and it is a partial overlapping as well. And this is full overlapping with the x square minus y square result into sigma bond formation from all the ligand 1, 2, 3 and 4. 1 and 3 with plus sign, 2 and 4 with minus sign. Similarly with px and ligand 1 and 3, 1 is positive, 3 is negative, and with ligand 2 and 4 py, ligand 2 is positive, 4 is negative. So all this pictorial representation will indicate the construction of LGO. So step 2 we learn. Now in step 3, let us form the molecular orbital and assign a wave function, quantum mechanical function to it. Once again, the linear combination of metal valence hybrid orbitals with the corresponding symmetry LGOs can lead to the molecular orbital expressions, as we can see into the example. This is first molecular orbital that is associated with 4s and symmetry label is A1G. So this is BMO bonding molecular orbital, and this star represent ABMO anti-bonding molecular orbital. N1 is the normalization constant, and this plus and minus sign indicates plus sign is for BMO, minus sign is for ABMO. This is metal symmetry and this is ligand symmetry. So all positive symbols are there. As you know that in s orbital all positive interaction is there. Similarly, second molecular orbital is for dz square. This is N2, second normalization constant, and ABMO and BMO is represented over here. That is another B1G. This is a partial interaction. This is complete overlapping, that is for dx square minus y square BMO and a BMO, and that can be represented in this way. Similarly, for doubly degenerate PX and PY, two wave functions associated with BMO and ABMO can be represented in this manner, and 4 and 5 are the normalization constant associated with this molecular orbital wave function quantum mechanically. Now step 4, that is construction of MOED, molecular orbital energy diagram. Finally, the energy level diagram incorporating all this information can be constructed as explained earlier. Figure in the next slide shows a qualitative molecular orbital energy diagram for an ML4 square planar complex. This is common, that's why I said ML4 square planar complex, where L is a pure sigma donor. Example you can take is tetraamino platinum plus 2 complex, and it is the best example to represent the MOED construction for only sigma interaction in square planar geometry. The energy sequence of the various orbital has been followed as sigma LGO, which is having the lowest energy BMO, n minus 1d, that is 3d atomic orbital of central metal ion. Then higher energy is 4s orbital of central metal ion, and highest energy is 4p atomic orbital of central metal ion. The ligand field parameters conforms delta 1, though the other parameters such as delta 2 and delta 3 are also shown into the figure, as we know that the splitting in square planar is much higher compared to the splitting in octahedral and tetrahedral geometry. So here all the delta 1, 2 and 3 will going to represent. So average splitting energy turns more higher comparing with octahedral and tetrahedral geometry. Delta 2 and delta 3 may be valid for metal ion for earlier transition metal series favoring square planar geometry in their complexes well. For the species such as tetraamino platinum plus 2, the 8 ligand sigma electrons which is donated by 4 amino group NH3. 3 is missing over here, that you need to keep in mind. It is a typological mistake. PNH34 plus 2. The 8 ligand sigma electrons are filled into 4 sigma molecular orbital such as A1G, EU and B1G. A1G is 1 molecular orbital, fill 2 electrons over there. EU is a doubly degenerate PX and PY, so 4 electron is there, and B1G 2 electrons would be there as well. So that way 8 electron donated by ligand group orbital will goes into this molecular orbitals, and the 8 electron, that is D8 of the platinum 2, will be we can enter into Eg orbital B2G and A1G of non-bonding molecular orbitals. A1U, sorry, it's not G, A1U. A1U non-bonding molecular orbital assumes slight anti-bonding character since it has the uh, right symmetry for the sigma interaction with the sigma LGO. The appropriate interaction are shown in MOED diagram by joining the lines. The B2G, that is HOMO, high occupied molecular orbital, that is non-bonding as well, and B1G, that is sigma star, which is lower occupied molecular orbital. Because the splitting energy is high, less electron will occupy into this, it is LUMO. So homo-LUMO concept is there. Separation is the actual ligand field parameters, that is delta 1, which can be estimated from the experimental results of the complexes. This is the construction of MOED. Here metal atomic orbitals are there. In between this molecular orbital, and last LGO, ligand orbital. We have 4 sigma ligand or group orbitals are there, having symmetry labels A1G, B1G and EU. And please note, the 4 sigma LGO has lower energy compared to 3D atomic orbital of central metal ion. That means 4 LGO remain closer to BMO. A1G is among the BMO having lowest energy, highest stability. Then EU, this is a typological mistake, I have corrected out over here. EU, PX and PY uh, having higher energy compared to A1G, and B1G is little higher compared to this. And this B1G, where we have two kind of interaction, dx square minus y square, and partial interaction with dz square as well, that represent BMO. Since BMO remain closer to these 4 sigma LGO, they will represent ligand characteristic. While here EG, that is DXZ and YZ, which have zero interaction because ligand approaching to axial side, not planar side. So they are purely non-bonding molecular orbital, and its energy is quite similar with the energy of atomic orbital of central metal ion, that is 3D. So their energy is completely similar. It is non-bonding. A1G is little bit anti-bonding as well as non-bonding in character. So here A1G symmetry is shown over here. That is B1G, not A1G actually. That is B1G of dz square. Non-bonding as well as sigma star. And the splitting difference between A1G and EG would be shown here as delta 3. Higher than A1G, we have B2G. That is a B2G that is completely non-bonding, and the difference, energy difference between B2G and A1G represented over here as delta 2, another splitting energy. And the other one, that is B1G star, that is B1G star for with dx square minus y square and dz square, partial interaction is there, and the energy gap between B2G and B1G is represented by delta 1. So the splitting total energy in square planar complex is represented by the average of delta 1, delta 2, delta 3, and that compared to octahedral and tetrahedral geometries, only sigma interaction, this splitting energy is much higher, and that is why most time in square planar geometry the complex is going to be low spin complex, and more electron will refill into this non-bonding molecular orbital, which is going to be HOMO, and less electron will enter because of the high splitting energy, major energy gap between these two. Less electron enter into B1G. So this molecular orbital is symbolized as LUMO, low occupied molecular orbital. Higher than that, we have 4s orbital of atomic orbital of central metal ion, and usse zyada energy, that is of A1G sigma anti-bonding orbital. As there is no ligand on z axis, pz, which is symbolized as a symmetric symbol as A2U, act as non-bonding. Pz is not going to participate into any overlapping since it will not contain any ligands on it. So pz orbital shown over here as a symmetric symbol A2U as non-bonding, and px and py which are having EU symmetry unzeroed, EU doubly degenerate is anti-bonding and highest energetic. Since all electrons are refilled from the d orbitals of central metal ion, because metal here is not a donor, uh, and it is a pi base in nature, pi acidic in nature, it has all the electron into Eg. So Eg electron represent metal characteristic in this MOED diagram of uh, tetraaminoplatinum 2 complex. So when we discuss regarding tetraaminoplatinum plus 2 complex, 8 electron from this 4 LGO is donated to this BMO, D8 configuration of metal. So all 8 electron will enter into this lower energetic Eg and A1G, and that is why it is HOMO, high occupied molecular orbital. Less electron enter into this. These are all empty vacant orbital, higher in energy, less stability. They represent a metallic characteristic, and this will represent ligand characteristic in this MOED diagram of square planar only sigma interaction. As we as will be seen later in pi bonding when we'll learn in pi interaction in square planar geometry in our upcoming next lecture, the other unused metal valence orbital in sigma bonding treatment have been shown as non-bonding molecular orbitals. They are A2U from p orbital, that is pz, already I have discussed, that is a non-bonding A2U. P2G, that is dxy, B2G, that is dxy, that is non-bonding as well, there is no interaction with ligand, and EG dxz and yz, EG is completely non-bonding in character. Well, thank you very much for paying attention to this lecture, and please mark your activity in Moodle as your activity mark is considered as your attendance. I request you to please mark the activity completion. This is for sigma interaction. This much is from my side. If you have any question, any doubt, any query, feel free to ask anything on either the chat box or either you can